Hello everybody, in this lecture we will be solving 1995 IMO problem number 1. Here's a view of this problem. 4 points A, B, C, D in that order are given on a line. So let me draw this line like that. And then we have A, B, C, and D. And the circles with diameters AC and BD intersect at X and Y. So let me make some space here. So we need circles with diameters AC. That would be the one with diameter AC. So C is here. And then with diameter BD, probably something like that. And they would intersect at the points X and Y. So therefore, if I draw the full circle like that and like that, so the points, probably the second one will be slightly smaller, right? So like that, I guess. Okay, so that would be the points X and Y. Okay, and the line XY, it would meet BC at Z. So let's go ahead and draw that line as well. So we know that this line, which happens to be the radical axis of these two circles, right? So that would be a 90-degree angle, and the point of intersection is Z. P is a point on XY other than Z. So anywhere on this line segment, let's assume it is somewhere here. That's my point P. The line CP, okay, so let's pick up a different color. So a line PC like that would intersect the circle with diameter AC. So I should go a little bit further. Yes, at the point, I think M, at C and M. Okay, so that's the point M. And similarly, the line BP will, like that, will intersect the circle with diameter BD. So let's call these circles as omega 1 and omega 2 because I will make use of these a lot, I guess. So this point is N, and we need to prove that the lines AM, so namely this line, so let's use another color now. So this line AM and then DN, that so obviously they would intersect at some place. Oh, and then show that this point of intersection happens to be actually on this line, on the radical axis of omega 1 and omega 2. Obviously, my sketch is not very neat, but at least that gives me the ideas. I would like to make use of radical axis theorem. So it seems natural that if I can show, that the points A, M, N, and D are concyclic, I claim that would be enough to provide this result. And the reason is the following. If truly AM and D is a circle, defines a circle, call this circle as omega 3. So you have a circle which goes through those 4 points, A, M, N, and D. In that case, the radical axis of omega 1 and omega 3 would simply be omega 1 is here and omega 3, so it would be basically AM, the line AM. And in a similar way, the radical axis of omega 2 and omega 3 would be ND, but then the radical axis of omega 1 and omega 2, we already know it's XY. As a result, by the radical axis theorem, those three radical axes should merge at the radical center of these three circles. So this is a very well-known result. So the rest of the problem is just angle chasing and proving that, in fact, those 4 points are concyclic. You can easily observe a much easier four cyclic points. In fact, the 4 points, I make the following claim. Let's begin. The points M, B, C, N are concyclic, and this is actually USAMO 2009 problem number 1 as well, I guess. But those 4 points are, it's easy to show that those 4 points are concyclic by just using the converse of a power of a point. And the logic will go something like this. So I don't need this part of the picture, so let me just get rid of this, I guess. Okay, so so the proof is as follows. So if you look at the power of point P with respect to omega 1, that would give me that MP times PC, but it's also equal to PX times PY. So that's obvious by, so this is pop of omega 1 at P, but Px times Py, if you look at the power of point P with respect to omega 2, and that's the power of point P with respect to omega 2 as well, and it can be written alternatively as Bp times Pn, yes, sorry for that, Pn. So this one comes from pop applied to circle omega 2 evaluated at point P. Typo, it's Bp times Pn, not Bn again, sorry for that. So let's just erase this, Bp times Pn. This is the power of point P with respect to circle omega 2. But now this immediately gives us the desired result that M, C, B, and N are concyclic by the converse of power of a point theorem. And this will help me in terms of the angle chasing that I need. So consider this, if I add this line here, I observe that angle MNB, this angle here, is equal to angle MCB, because those 4 points are concyclic, and those two angles, they subtend the arc MB of this new circle. That's, if you will, let me just draw that circle just in case we might need it. So that you don't forget those 4 points are cyclic. Okay, good. So therefore it's obvious that those two angles are equal. And we also have that triangle AMC, because it subtends the diameter. This angle here, AMC, is 90 degrees. And as a result, MCB, the angle MCB is 90 minus angle MAB, right? So this is 90 minus, so this angle here is 90 minus the other angle, so suggesting that this type of angle plus this type of angle is equal to 90 degrees. Consider triangle AMC. Similar way, triangle BND is a right triangle where angle BND is 90 degrees. As a result, angle MND is equal to angle MNB, so this double strike angle, plus angle BND, which is, we know, is 90 degrees. So it is just angle MNB plus 90 degrees, right? So compare these two angles. So let's write those two angles again. So angle MAD is simply equal to, we agreed that it was 90 minus this angle here, which is the same as this angle. So it is 90 degrees minus MNB, angle MNB. And on the other hand, we just have proved also that angle MND is equal to 90 degrees plus angle MNB. So therefore those two angles, MAD plus angle MND, combining these two results, this angle plus this angle is simply equal to 90 plus 90 is 180. And minus MNB plus MNB, they cancel out, and boom. So we have that these two angles, angle MAD and angle MND, are supplementary angles. They add up to 180 degrees. As a result, we proved the claim that these 4 points, A, M, and D, are concyclic. As a result, there exists a fourth circle which goes through those points. We decided to call that circle as omega 3 early on. As a result, those three lines which we want to show as concurrent are each the radical axes of pairs of these three circles, and by the radical axis theorem, they should meet at the radical center of these three circles, which is basically this point here. And we are done with this solution. Hope to see you on next video.